Let's start by trying to answer the question, why does substitution as a method of integration work? Why does substitution work? We'll ultimately try to explain it in the abstract, but it's easier if you think about it alongside a specific example to help you understand it. So the specific example that we'll think about to help us understand substitution is integrating 3x squared cosine of x cubed. Now, if you didn't think about and practice doing integrals very much, you think back to even 2 weeks ago, this integral looks pretty hard to do, but it's not too hard to do because you notice if you let w equal x cubed, then dw will be 3x squared dx. This will be a fairly simple integral. Let me go ahead and write that out. Let w equal x cubed, dw will be 3x squared dx. And this integral will therefore become the integral of cosine of w dw. That's fairly simple to do. You get sine of w plus c. And then don't forget to go back to x. So you get sine of x cubed plus c. It's really a simple enough integral that you could do it by guessing. But if you want to show your work, as I ask you to do on the homework, you should show the substitution. I'll use w. You can also use u. What is the abstract form of what we're doing here? So here's our specific example. What's the abstract form of this? Abstract form. We're integrating a function that can be found by differentiating some other function using the chain rule. Think about checking this answer here. You'd use the chain rule. Outside function is the sine function. Inside function is x cubed. Chain rule says differentiate the outside function, sine, to get cosine. Plug in the inside function, so you get cosine of x cubed. Then multiply times the derivative of the inside function, 3x squared. This function that we integrated here could be thought of as, well, this is a composition f of g of x, and this is the derivative of g of x. That's g prime right there. And this function here is also a composition, but the outside function is not the same as the outside function here. The outside function up here was cosine. Little f of x is cosine of x. But sine is a function whose derivative is cosine. I'll call it capital F of g of x. The g of x function, the x cubed, is still the same. When you differentiate this, you're going to get the function we integrated there. So yes, in the abstract, what we're doing is we're integrating, let me write it in this order, little f of g of x times g prime of x dx. We're letting w equal the g of x. dw is g prime of x dx. If I make those substitutions, this becomes the integral of f of w dw. Now, of course, sometimes substitution is a little trickier than this, and you have to account for multiplicative constants and that kind of thing. But in the simplest situation, it works out like this. If capital F is an antiderivative of little f, this then becomes capital F of w plus c. But then go back and replace w with g of x. And you see that the form of the answer that we get matches the form of the answer that we got for the specific example over here. And if you check this by differentiation, using the chain rule, the derivative is capital F prime of g of x times g prime of x, but capital F prime is little f. I'm assuming that. In writing this equality right there, I was assuming capital F prime of W equals little f of W. That's what it means. It's an antiderivative of little f. So you see, we got the exact same kind of thing happen here in the abstract that we had happen here with this specific example. So you could say this is an explanation for why it works in the abstract. A bit harder is to explain why it works with definite integrals. For the specific example here, let's make it a definite integral. Let's say we're doing the definite integral from 0 to, how about cube root of pi over 2, which seems like a really weird number to pick until you realize that because our substitution is W equals x cubed, when we change the limits of integration, that cube root is going to go away because we're going to cube it. We still let W equal x cubed. dW is still 3x squared dx. We still get the integral of cosine of W dW, but now change the limits of integration. I happen to pick the lower limit to be 0, so that actually doesn't change because 0 cubed is 0. If I pick something non-zero there, it would change. But 0 cubed is itself, so it stays 0. This thing cubed becomes pi over 2. And like I emphasized, what was it, last Friday or on Monday? If you're going to write an equal sign here, you must change the limits of integration. I'm insisting on that to get full credit when I ask you this kind of thing on exam 1, as I probably will. Got to change the limits of integration. Some people don't. That's sloppy. They still can sometimes get the right final answer. It's like 2 wrongs making a right. But just because 2 wrongs made a right doesn't mean the wrongs were right. They were still wrong. Don't do it. They're not equal unless you change the limits of integration. Once you've changed those limits, now use the fundamental theorem, and you never have to go back to x. That's kind of nice. So we get sine of pi over 2 minus sine of 0 is 1 minus 0 is 1. The final answer is nice. It's 1. By the way, changing the limits of integration like this has a benefit beyond just being right. It's also useful, especially in multivariable calculus, when you're doing double integrals, for example, and you are using polar coordinates. If you don't get in the habit of changing the limits of integration right now, you're going to get into trouble in multivariable calculus. You'll almost always get the wrong answer. So change the limits of integration. How does this work out in the abstract? Once again, we are integrating a function of the form f of g of x times g prime of x. But now it's a definite integral, say from a to b. How does substitution work out here in the abstract if we let w equal g of x? So that once again, dw is g prime of x dx. And I do end up integrating then f of w dw, but now, if I'm going to say these are equal, I have to change the limits of integration, and I have an abstract g of x. I am not specifying what g of x is, but it is some function. You have to change the limits of integration using that function. When x is a, w will be g of a. And when x is b, w will be g of b. So the thing we're saying is that these two integrals, these two definite integrals are equal. But we really haven't proved it. Why does that work? It's still related to the chain rule, just like before. But it also relies on the fundamental theorem of calculus, applied a couple times, actually. Let's apply the FTC to say what this equals. So we're claiming these are equal, but let me put a question mark here, indicating I'm unsure that they're really equal in general. What is that equal to? The fundamental theorem of calculus would say, if I can find an antiderivative of little f, call it capital F. I have to do that kind of thing where what do? I plug in the limits of integration. I plug in the top limit, the upper limit here, plug in the lower limit here. The upper limit is g of b. It's a function of b, but remember, b is a specific number and g is a specific function. So this is a specific number, g of b. And the lower limit is g of a. So that integral equals this, where, once again, capital F prime of w equals little f of w. Capital F is assumed to be an antiderivative of little f. If these two integrals are going to be the same as I claim they are, this integral up here is better equal the same thing. Can I apply the FTC there as well? I applied the FTC here, part 1 from chapter 5. Can I apply the FTC to that one? I would need an antiderivative of this thing. It's a more complicated function. But it's just like what I did up here. I know the answer, it's that. It's the chain rule in reverse. Capital F of g of x is an antiderivative of this thing by the chain rule. So I can apply to the FTC to that. Capital F of g is your antiderivative. I've got to plug in the limits of integration. They are a and b. Plug in the upper limit here and the lower limit there. And lo and behold, we get the exact same thing. We are happy. That is why they are equal. Applying the FTC to both sides, and with one side also using the chain rule. And in both cases, I'm assuming capital F prime of a number equals little f of that same number.